All right, this is number 2 on lesson 9.5. We're going to do the traditional method of hypothesis testing. Here we have the number of days missed before a program of work, and this is the number of days they missed after going through the program. Our 3 formulas we're going to use today when we have small dependent samples. It's a small sample, so you can use a t-score. What we're going to be looking at is the differences between these numbers. Okay? S sub d, that means the standard deviation of the differences. D bar, that's the average difference. Bar means average here. Okay? And then we're going to have to get that information before we can find the t-score up here. Notice we need to find d bar before we can plug it in up here. We need to find the standard deviation of the differences before we can plug it in right there. Okay? So the first thing we do is we go through and we subtract these to find the difference between each of these values. So we're going to find d by doing x sub 1 minus x sub 2. So we're just going to subtract. So 2 minus 1 would be 1, 3 minus 4, negative 1, 6 minus 3, 3, etc. Just going to write them all down. Did I make any mistakes? Look right. Next, I'm going to figure out the average difference. So to get the mean difference, which is d bar, I'm going to add up all the d's, all the differences, and then divide by the number of differences that were work. So to add this up, 1 plus negative 1, that would be 0, 3, plus negative 1 is 2, 3, 5, 7, 8, plus negative 1 is 7. So when I add those up, I get 7. How many differences were there? 6, 7, 8, 9, 10, right? So in other words, on average, the change in the differences was 7/10 of a day, or we'll just call it 0.7. So d bar, just write it over here, d bar, the average change in the days missed is 0.7 days. Next, we're going to need to find the standard deviation of the differences. We're going to have to sum the d squareds. So we're going to have, these are my d's here, square all these. So what do you get when you square a number? What type of answer do you always get? Positive, yeah. So you're always going to get positive. So 1 squared is 1, negative 1 squared is 1, 3 squared is 9, negative 1 squared is 1, 1, 4, 4, 1, 1, 0. We're going to sum those up. So add them together. Sum of the d squareds. So 1, 2, 11, 12, 13, 17, 21, 22, 23. That's the sum of the d squareds. All right, we've kind of got our information we need there, I think. Let's go ahead and start our steps now for number 2. Step A, we're going to write our null and our alternative hypothesis. It's going to be a little bit different than what we're used to. Here's the problem one more time. A program for reducing the number of days missed by food handlers in a certain restaurant chain was conducted. The owners hypothesized that after the program, the workers would miss fewer days and work due to illness. The table shows the number of days 10 workers missed per month before and after completing the program. Is there enough evidence to support the claim? The claim is that they would miss fewer days at alpha equal 0.05. Let's write that down somewhere. So the claim is they're going to miss fewer days. If they miss fewer days, for example, this worker missed fewer days. He went from 2 down to 1. If he missed fewer days and you subtract, what type of a difference are you going to get? A positive number, right? If this number goes down and then you subtract, you get positive. If it goes up, like this worker missed more days after the program, then you get a negative. So if they missed fewer days, then your difference is going to be a positive number. So in other words, your mean difference is going to be positive or greater than 0. If the average difference is greater than 0, then that would mean that the program worked and that people are missing fewer days. That's the claim. The null then would be that the average difference, mu sub d, would be less than or equal to 0. So it's a little different way to write. You kind of have to think about it before you write it. Now notice we got a mean difference of 0.7, so that's positive. So you might think, okay, we know they missed fewer days. But maybe this is just due to sampling error. Maybe it just happened to be the 10 people we picked and did the experiment on. Maybe 0.7 is too close to 0 that we can't really say there was a change in behavior because of the program. So we'll go to step B. Step B is get the critical values. We're using a t-distribution because we're doing a small sample, and the samples or the individuals are dependent because each of this is the same person. This is person 1, person 2, person 3. Okay? Dependent because you might have a person who's has a tendency to miss a lot of days, like this person right here. If they missed 7 before, they have a tendency to miss a lot after they go through the program too. So there's some dependency because we're using the same person. This is a t-distribution. Mean of 0 in the middle. Alpha equals 0.05. Right-tailed or left-tailed? Right-tailed because it points right. So this is our alpha out here. You go to your t-chart. And degrees of freedom on this is back to n-1 again. So if we have 10 people here, 10 minus 1 is 9. You know, degrees of freedom of 9. Then you're going to look across at the one-tailed. You look at one-tailed at the top on your t-distribution chart. Look for alpha equal 0.05.
1.833.
1.833. So our critical value up here is t equals 1.833. Any questions about that? Okay, keep moving here then. Now, we want to find our t-score next, but we can't find our t-score until we have our d-bar, which we have, it's 0.7, and we have the standard deviation of the differences. We don't have that yet. So I'd say that's our next step for part C. Let's find the standard deviation of the differences. That says you take the square root of the sum of d squareds. What's the sum of the d squareds equal? 23. Yep, so you're going to take 23 minus the sum of your d's and square that. So the sum of the d's was actually this number right here, 7. Right there, I did the sum of the d's was 7. So 7 quantity squared. So notice the difference here. Here you square all the d's, then you sum them up. Here you sum the d's and then square that answer. Divided by n. N is the number of people here, so there's 10 people. N equals 10. And that's all divided by n minus 1. 10 minus 1 would be 9, right? Might need a little help with the calculator here. So let's say I do some of this without, though. I've got 23 minus, this would be 49 divided by 10 would be 4.9 divided by 9. So I need you to take 23 minus 4.9 divided by 9, then take the square root. See what you come out with. Notice I squared the 7, that's 49 divided by 10. That's how I got the 4.9. Anyone get an answer? 2.418. 2.418? Anyone else get that?
How come we can't just type those in another stack? The differences.
You probably could.
Yeah, I did.
The same thing? Yeah, you probably could. Yep. I'm kind of showing it without using the calculator a lot, but there's probably some other ways I could help you shorten it with the calculator, which I might show in the next example. Okay, next. Now we find our t-score, which is up there. D-bar, which we said was 0.7, minus mu sub d, which we're hypothesizing that that could be 0, right? Up in the null. So that's going to be 0. Divided by standard deviation of the differences, which is 1.418. Divided by the square root of n, square root of 10. So make sure you put parentheses here, and you probably need parentheses here. So it's 0.7 divided by this.
What's the 0?
What's your question?
I was saying, what's the 0 represent?
That mu sub d is, in the null we always said that that could equal 0. There'll always be a possibility of that equaling 0, so we're always going to put a 0 there. What's that come out to then?
1.56.
1.56. So there's our test value. Our test value would fall, 1.56 would fall about right there, somewhere between 0 and 1.8. So it's out in the white area, or it's right here on the, we're in the white non-rejection region. So step D, do not reject the null. So if we're not rejecting the null, that means we think it's true, which means we think the alternative hypothesis is probably false. So what should we say about the claim? Right. So there is not enough evidence to support the claim that workers miss less days after the program. Now someone might argue that and say, well, hold it. They missed an average of 0.7, these 10 people missed an average of 0.7 days less after they went through this program. Doesn't that prove that the program worked? No, because there's sampling error you have to take into account. We only sampled 10 people. We're trying to make a hypothesis about the entire population of all workers out there that might go through this program. There's not enough evidence here to support this claim that this program works. Okay? Even though you might think it does, the evidence statistically doesn't really support that. You can shut that off.